I, so I think almost everybody knows me that's on this listening to this presentation tonight. I'm a lifelong system engineer, and when I think about a problem, I think about it in a very, very big context. So what we're going to be looking at tonight is 6 meters, starting with the physics, and then looking at practical limitations, and then we'll look at some of the products that are available in the marketplace, both things that can be purchased and things that are well documented and that can be built, and then some of the issues. Because as soon as you put up a new antenna, no matter how well it works, as soon as the installation is done, it starts degrading. So we'll talk about how to slow that process down. Okay. So this photograph is my favorite 6 meter antenna these days. It's an 11 element Yagi, 50 feet high. I kind of backed into that 50-foot height. It's kind of an available space on that 150-foot rotating tower. But boy, am I happy with that height. It really, really works. I've had this antenna for 2 years. And the first year I had it, I worked 500 Europeans and 100 JAs. And I thought I could never do that again. And then last summer, I worked 500 more Europeans and 100 more JAs. So this thing is just incredible. And you don't need an antenna this big. I think the real trick is to get it at the right height. I'm sure if I had a 7 element Yagi at this height, I wouldn't be able to tell the difference. And as a matter of fact, my neighbor, W3UR, has a 7 element 6 meter Yagi at 70 feet, and our performance seems to be about identical. Well, this is the first thing I always recommend that anyone buy who's interested in selecting antennas, building antennas, understanding how they work. If you don't have this on your shelf, and if you haven't read it, doesn't do any good if it's just on your shelf, you should. It's by far the best reference out there for hymns. Has everything you could possibly need to know about antennas for the radio amateur. So let's start with physics. And unless we understand sporadic E, which is the dominant form of propagation available to us on 6 meters, we can't possibly understand what sort of an antenna we should use to capitalize on sporadic E. So sporadic E is fundamentally different than the HF propagation that we use for the most part. Almost all the HF propagation is via the F layer, or more correctly called the F region. It's too thick to be called a layer accurately, or the E region. But sporadic E and the propagation we use on HF is ionized by the sun. Well, sporadic E, the dominant form of propagation on 6, is not ionized by the sun at all. It's caused by tons and tons of meteoroids that come into the Earth every day, and they're ionized by heat as they enter the atmosphere. And unlike the electrons and ions that are ionized by the sun, these electrons and ions are long-living. They last for hours or even as long as a day, or maybe sometimes more. And what it looks like overhead, over us, is a dense, thin patch. And we're talking about 6 meters now. It does not appear as a continuous layer on 6 meters. It never does. It appears as patches of ionization and both ions and electrons, and they have to exist together. So unlike, for example, the E region propagation that we're used to on 40 meters during the day, on field day, for example, or any other daytime contest where you can work in any direction at any time, on 6 meters, you're totally dependent upon these ionization patches and where they happen to be. But it's very predictable in terms of what their elevation above the ground is. They're about 100 kilometers above the Earth. And that doesn't vary very much. Probably about as low as they ever get is about 95 kilometers, and about as high as they get is about 120. So you can determine what the angle of radiation is with a little bit of geometry. You don't have to guess where the reflecting layer is, because it's at a very predictable place. And the sporadic E patches, and I'll always refer to them as patches because the contact here is 6 meters. When you get down to 20 meters, sporadic E does in fact exist more or less as a layer, but on 6 meters, it's only patches. So these patches sit on top of the atmosphere, and they're affected by atmospheric tides, just like as if the atmosphere were an ocean. So these patches get affected and become more dense depending on the atmospheric tides that are sitting under them. And then there are wind shears, these seasonal winds, predominantly in June and July. There are westerly winds just below where these patches are, and easterly winds just above. And there are wind shears in between. And those wind shears are also cause the patches to become more dense and force their usable frequency to go up. And then to further complicate things, there are other effects, which I won't get into. They're more secondary than the ones I just mentioned. Wind shears and tides are the major ones. And the other thing is that all of this exists in the context of the Earth's magnetic field, which constrains the movement of these patches and usually causes them to gradually drift south to north, very slowly normally. So this is kind of the context. And so if anyone asks you, well, what do you know about the angle of radiation needed for your antenna? You know, because you know the height of the ionosphere. There's no guesswork. You just need to know where the station is you want to be able to work, and you can determine the angle of radiation that you need. So the most common form of propagation, and usually the one that most of us discover, because it's much more prevalent than any of the others, is simple single hop sporadic E. It's extremely efficient. Signals often sound like local stations, but it doesn't cover a very big slice of geography. Typically, it covers distances from about 800 to 1,200 miles from our location, sometimes closer from here in Maryland, maybe sometimes up into northern Maine, and sometimes a little bit further. But signals are usually quite strong, but it's also patches. So this morning, we might be able to work stations in Florida, and this afternoon, the Florida stations might be gone. In fact, in 5 minutes, they might be gone. And we might only be able to work into Missouri. It's all dependent on the location of these patches. But as anyone who gets on 6 meters discovers, there's more to 6 meter sporadic E than single hop. And we start noticing that we will occasionally hear stations in California or down in the Caribbean or on the north coast of South America. And that is usually double hop. Doesn't have to be though. But usually it is, because it's the sporadic E patches are very efficient, so they're very low loss, but the intermediate ground reflection is quite lossy. So, but the combination works out pretty well, so that most of the propagation out to about 2,400 miles is, so that's California for us, or the northern tier of South America. That's usually double hop. But it can be another mode, which I'll show you right now. And this is the propagation mode that allows us to work most of the world. Not all the world, but most of it. It's actually operating above the MUF. And what happens when you operate above the MUF for these ionization patches is that instead of having the propagation come back to the Earth, I'll just use my pointer here. So for double hop or single hop, propagation will go up to the cloud and come back to the Earth. But if we're operating just above the MUF of these ionization clouds, the propagation instead doesn't reflect as much. And it carries a course through the ionosphere. And if it encounters another ionization patch, it can then come back to the ground. Oops. So that's the mode of operation here. And the reason why these very long distance chordal hops are not that rare. These are actually patches that we wouldn't be able to operate on for single hop or double hop because the MUF is just below 6 meters, probably around 45 megahertz or so. And it can be many hops. This literally can, well, I mentioned I've worked more than 200 Japanese stations in the last 2 years. So that's about 7,000 miles. And this past summer, we had some days of really remarkable propagation into the Persian Gulf. And I worked a couple dozen stations in the Persian Gulf this summer, mostly in June. That was a big surprise. I've never worked any stations in the Persian Gulf at all. And then suddenly this year, these patches happened to be in the right place and the propagation was there. The year before that, using the same 50-foot high antenna, I worked a station in Kazakhstan, 200 miles from the Chinese border. So this propagation is quite remarkable, and the mode is above the MUF partial reflection. But let's take a look at when these patches of ionization actually occur. This is a little bit of a complex chart, and what these colors are showing is not intensity, it's frequency of occurrence. So on the right-hand side here, you can see the very dark color shows that the most frequent occurrence rate, about 40% of the patches, occur at an altitude of 105 kilometers and at around 10 o'clock in the morning. But more significantly, what it shows from these actual measurements is that during this June-July period, the ionization patches begin at sunrise. They intensify, this is all statistical in nature, they intensify around 10 o'clock in the morning and gradually fade away until about 3 o'clock in the afternoon. That set of patches goes away, and then there's another distinct period of sporadic propagation that occurs in the late afternoon and evening. The probabilities are a little bit lower, but this is on the right-hand side here, this is the afternoon and evening, up as late as midnight, sporadic ionization that allows us mostly to work into California or to work into Japan. And you can see the statistics here. The opening typically begins with patches forming up at about 110 kilometers. And then these winds that are responsible for the creation of these patches gradually causes most of the patches to drift down to about 100 kilometers and sometimes a little bit lower. And this is a characteristic primarily present in June and July. These atmospheric winds are not as reliable after you get out of that period, and sporadic becomes less common. And here's another look at some scientific measurements. And this is a really different way. If you recall, the cause of ionization for sporadic is meteoroids. So this is meteor dust, microscopic particles. But the occurrence of this meteor dust occurs coincidental with the larger meteors that come into the atmosphere. And this chart shows what time of year you can't measure the meteorites. They're too small to measure in terms of how often they occur. But you can measure the occurrence of meteors during the course of the year. And you can see from this chart that around the middle of May, the occurrence of meteors peaks. It peaks right around July 1st, and then gradually declines until the middle of August. Very slowly, though, the occurrence of meteors and meteorites declines. And the point of this chart is on the blue side is the average meteor count, and the orange color is the critical frequency of these sporadic patches that are measured using vertical incidence sounders. I'll describe that in just a moment as to what the significance of that is. But the important takeaway from this chart is that the occurrence of meteors from mid-May to mid-August coincides very accurately with the maximum frequency for vertical propagation in the sporadic layer. Tightly correlated. And one other look at the occurrence of meteors, and this is time of day. And these are meteors again, because they're easier to measure, but the meteoroids have the same occurrence. You can see here when our location is facing, well, when sunrise is occurring at our location, we're facing into the sun. And that's the optimum time for high-speed meteors to encounter the Earth. So they have more energy, so they get hotter when they enter the atmosphere. And that occurs between roughly 2 hours before to 2 hours after local sunrise. And gradually, as the day declines, the occurrence of meteors and meteorites fades away until they reach their minimum at sunset. But recall what I said earlier, that the electrons and ions that are stripped out of these meteoroids, they last for hours. So even though they tend to get created a little bit more early morning, when these openings begin, the sporadic E patches can continue to get formed all day long as these east and west winds and the wind shears cause those electrons and ions to get pushed together. Okay, so that's enough of the physics, describing a little bit of the physics that explains some of the unexpected behavior when we first experienced 6 meters. But here's some more aspects that are very easily observed when you first get on the band. One thing is that the ground footprint for propagation of sporadic E is smaller than we used to on the HF bands. On 6 meters, generally, when we have an opening, let's say into Chicago, the opening is usually several thousand square miles, and sometimes it can be as much as 10,000 square miles or a little bit more, but it's very definitely regional. We won't normally be working into Chicago and then have the opening extend into Missouri and into Arkansas. It just doesn't happen. The opening is constrained. But over the course of time, very often these patches drift south to north very slowly. And the opening that was in Chicago, if the ionization continues, doesn't always continue, but if it does, it might drift northward into Wisconsin, for example. And what about these openings? Well, they occur every day in June and July. And then you might say, but wait a minute, Frank, I can remember days I've turned my radio on in June and July and I heard no opening at all. Well, even though these openings occur every day, frustratingly, they might not occur for you every day. So there will be occasions when we can look on PSK Reporter and see our friends up in Philadelphia working one after another QSO into Japan, and we can't hear any of them. Can't hear any, and we're only 100 miles away. So the 6 meter band does have sporadic E propagation patches every day in June and July, but not necessarily where we are, or not necessarily at the time that it's convenient for us to turn the radio on. And also this very long distance propagation, 4,000 to 10,000 kilometers plus, occurs during many days in June and July. But just like the name of this propagation would suggest, sporadic, this long distance propagation is very sporadic. And unless you're prepared to live on your radio in June and July, and none of us are, it's very important that you form some cooperating arrangements with other hams in your region so that when these openings occur, that people will call you on the phone and alert you to their occurrence. Otherwise, you'll be chained to your chair from 6 a.m. till midnight every day for 2 months. And that's not fun. But if you can get together with half a dozen or a dozen or more friends and alert each other to the occurrence of these openings, it makes it a whole lot more fun. These very long distance openings occur very occasionally in late May and very occasionally in early August. And then they go away. And then there's a few days, mostly between Christmas and early January, where they occur. And they mostly occur into the South Pacific. And they're pretty darn uncommon. If you don't have a friend to alert you to them or a computer program to alert you to it, there's not much chance you'll ever catch these openings. My favorite one was Christmas. I guess it was about 6 years ago when K1 HTV called me on the phone at about 10 p.m. and told me that 6 meters was wide open into New Zealand. And sure enough, it was. And it was quite an experience. And the opening lasted about an hour. So preferred antenna, horizontal polarization is the only way to go. It's the way you get the best efficiency. I wouldn't ever recommend to anyone they use less than a 3-element beam. On this band, 3-element beams weigh about 10 pounds. I prefer that people use larger antennas. That I'm going to show you some very good ones. Preferred height, and I'll show you why, is 50 to 60 feet. 70 feet is okay, but it's not very good for domestic work, but it's fine for DXing. And if you can't put antennas that high, 25 feet works pretty well. It's only about 3 to 6 dB worse, so that's not ideal, but it's a whole lot better than not being on the band at all. So it's about 3 to 6 dB down compared to an antenna at 50 feet. But there is a problem here, and that is when your antenna is only 25 feet high, and Ted can tell you about this, it's very, very easy for it to get degraded by other nearby buildings. So there's a real issue if you're in a densely crowded suburban or urban neighborhood. If your antenna is only 25 feet high, it's going to be degraded pretty badly by all of the buildings and other things that are within 500 feet or 1,000 feet. So I already mentioned the monthly occurrence every day in June and July. Peak occurrence, the openings tend to begin right around sunrise, but that doesn't happen every day. They're much more frequent around 8 a.m. and they last through the day, slowly declining, and then there's another very noticeable peak in the evening. And that propagation tends to be to the west. And of course, all during this period, we can get openings into South America also. These sporadic key patches are frustrating in terms of their variability location. They're not always in the place we want them to be. So we have to be very opportunistic. And the day-to-day variation is very frustrating too. There tends to be a little bit of repetition from one day to the next, but not definitely not from one day to the second day. But sometimes when you have an opening on Monday, it's worthwhile taking a look on Tuesday because there's a small chance that you'll have an opening again, but it's by no means guaranteed. And the other thing about times, when we think about times, we talked about the occurrence of sporadic key from 6 a.m. until about midnight. Those times refer to the time at the location of the sporadic key patch, not to our local time. So it's the location where the ionization is. So if, for example, you're trying to figure out, well, when's the best time to work into Japan on 6 meters? Well, it has to be during daylight in Japan, and it's likely to be probably starting. Well, it could either start at their sunrise or any time after. Likely to be more like an hour or two after, and then. Unfortunately, the patches tend to change location. So usually what happens is we'll notice the beginning of the opening and it'll last a while. And then all of a sudden we realize that we don't have the opening anymore and it's shifted usually to our north. And the day to night variability is pretty extreme. There's really no correlation whatsoever between the openings we experience in the morning and the likelihood of an opening in the afternoon or the evening. So if, for example, we have a big opening into Europe in the morning, don't think that increases the likelihood of an opening to Japan in the afternoon, because it's a completely different mechanism that creates the afternoon sporadic key patches. So, and importantly, if you do not have an opening into Europe in the morning, do not assume that we will not have let's say, an opening to the west coast of the United States or an opening into Japan in the evening. You can get a tremendous opening to Japan in the evening and have nothing at all in the morning. And that's due to all this variability in terms of sporadic heat patch location and MUF variability. And one of the reasons that 6 meters is called the magic band is because there's all this variability, seconds to minutes to hours, and morning to evening, and day to day. And then between June and July and the rest of the year, tremendous variability. And some of these openings literally last just seconds. Fortunately, usually just long enough for one lucky person to complete an FT8 QSO, and then the band is gone. So that's one of the vexing aspects of this band. So K9LA wrote a very nice, easy to understand paper, and the URL is on this slide, and explains the physics of the elevation angle, or the angular radiation of an antenna, versus the MUF of these sporadic heat clouds. So let me take a moment to explain this term right here in the middle called FOES. This is the vertical critical frequency. What that means is if you're a ionospheric observatory, and thankfully these observatories are all over the world, and you're sounding vertically straight above us, this is the maximum frequency at which the sporadic E, and it's actually a layer at these lower frequencies rather than a patch, but it's the maximum frequency that the sporadic E layer will reflect the signal back down to the observatory. So that's called the vertical incidence critical frequency. And there's a relationship between the vertical incidence critical frequency and the low angle propagation that we're usually interested in. And it's simple. If you multiply the vertical incidence frequency by roughly 5, that will correspond to the low angle MUF. So a very important fact, and that is, if you look at this data from these observatories is available on the web, and you will discover during June and July, when these critical frequencies reach their maximum, that almost never will you see FOES, the vertical incidence critical frequency. It almost never exceeds 12 megahertz. So what does that say? That says you almost never see sporadic E patches with an MUF above 60 megahertz. Almost never. And you can convert that into the required, recall that you can determine the angle of radiation because we know the height of the sporadic E patches. It's 100 kilometers. It could be as high as 110, 115. So we can determine with geometry what the angle of elevation has to be to cover certain distances. So, for example, FOES rarely exceeds 12 megahertz. So if we look in this column right here, that means the FOES rarely produces an MUF above 60 megahertz. This shows 55 to 65. And the optimum antenna height to produce the required elevation angle for that relatively uncommon angle is 25 feet. But this occurs maybe once or twice a year. This is when you can work stations in northern Maine or storm stations in North Carolina. Doesn't happen very often. And most of us are more interested in distant stuff rather than optimizing our antennas to work into Maine. Nothing wrong with optimizing your antennas to work into Maine, but it happens only a couple times a year. So if we look at the lower FOES, below 12 megahertz, the FOES that is very frequent is between 10 and 11 megahertz, very frequent. And if you look at the single hop distance that's covered, it's roughly 1,200 to 1,400 kilometers is the optimum single hop distance. And that corresponds to an elevation angle of your antenna from 5 to 8 degrees above the horizon. So keep that in mind. That's a very important set of angles, 5 to 8 degrees And then angles above 8 degrees are much less important because there isn't enough ionization to support it. So, if we had propagation at 12 degrees, your 25-foot high antenna would work, but there very rarely is enough ionization in these patches to support the angles between, well, certainly as you approach 12 degrees. And then if you look at the really long distance stuff, where we intentionally intend to operate just above the MUF. So if we look at the MUF at 45 megahertz and we want to use this partial reflection stuff, that's going to correspond to antenna elevation angles below 5 degrees. So this is going to determine how we decide what height our antennas should be at if we can. That's not to suggest your antenna at 25 feet won't work for the longer distance DX. It will work, but it just won't be optimal. So for the rest of my discussion, we're going to be talking about practical antennas that exploit all these characteristics we've discussed. And all of the gain figures that I'll quote for some of these example antennas are all gain compared to a half wavelength dipole in free space. And many of us have heard that a half wavelength dipole in free space has 2.15 dB gain over this theoretical isotropic radiator. And why is that? Well, there's essentially no radiation off the end of a dipole antenna. So it has gain because the radiation from the antenna is concentrated broadside from the antenna. And if it's in free space, it doesn't have any elevation lobes, so it's a donut shape. So this donut shape, and you can compute this in any antenna modeling program, has a 2.15 dB gain over isotropic. So this is what we'll use as a dipole in free space as our reference. And all the antenna modeling programs work this way as far as I'm aware. So let's look at some antennas. This is a modest size 6-meter Yagi, 5 elements on about a 14-foot boom, 50 feet high, which is an excellent height for almost all propagation via sporadic E patches. There is a case, though, where this antenna can be too low, and that is if you're in a dense housing area, let's say more than one house per acre, then this height might not be the best choice because there'll be some degradation, and I'll try to put some figures on that in a moment. But this is an excellent height for those of us who are in less dense, crowded areas where we don't have to get up above all of the clutter from houses. And why are we worried about houses? Because they contain things like heating ducts. They contain electrical wiring. There was a time when they contained telephone wiring. They contain Ethernet cables and all kinds of other conductive stuff. So even though houses are normally not made out of a steel box, they have lots of stuff inside that is physically substantial, especially compared to 6 meters. So let's look at this antenna. It's 50 feet high, so its maximum gain is at exactly the sweet spot. It's at 5 degrees elevation angle, and its 3 dB points are at 3 degrees elevation and 8 degrees elevation. So if you remember that chart I showed you before, this is why the 50-foot high antenna, not in a crowded neighborhood, is really the optimum choice because it provides very good coverage down below 5 degrees for Europeans and Africans and Pacific stations. And it provides good coverage above 5 degrees if we want to chase grids. So it covers that. It does have a null, but the null occurs at these angles above 8 degrees where sporadic E clouds rarely will allow signals in this null to be propagated at all anyway. So we're not wasting energy at angles that are rare. And when they are present, it only allows us to work into Maine or North Carolina. There's a secondary lobe from this antenna, and it does provide coverage, but not very often. It's way up at 15 degrees. So even with this antenna, we will be able to work some of that closer in stuff. And then for the much higher angles above 20 degrees, sporadic E clouds never, ever support angles above 20 degrees. So this is just wasted energy up here. So this is the 50-foot high antenna. This is kind of the sweet spot unless you're in WA3AER's location where even 50 feet isn't quite enough. So let's go ahead and put this antenna up at 70 feet. This is an excellent height if you're a DXer. So if you don't care about chasing grids on 6 meters, if you don't care about getting into VHF contests, and all you really care about is working the DX opening, this is a really good height. This is also a good height if you're in an area with a lot of dense housing, because the antenna gets up above all that clutter. So even though it's not an ideal height, like 50 feet or 60 feet might be, in an area with dense housing, this higher height can be beneficial because it gets out of all the clutter. You can see why this is mostly a DXing antenna, because the main low angle lobe covers between 2 degrees at 3 dB points, maximum radiation at 4 degrees, and then it's already declining at 6 degrees elevation angle. So this is very definitely a DXer's antenna, and all these angles between 6 degrees and 10 degrees or so, where you want to work grids out in the middle of the US, well, you don't have any energy there. So you're going to be suffering compared to the guys with antennas down at 50 feet. But if you're a DXer, you don't care about working Illinois or Missouri. So let's go all the way down to 25 feet. And why might we want to do that? Well, if you're doing grid expeditions, for example, or if you're going on field day, it might be too inconvenient to put an antenna up at 50 feet. So if we look at the radiation from the same antenna at 25 feet, well, I can still work DX with this antenna. I'm only 3 dB down at this 5 degree elevation angle where I can work long distance QSOs. And it's really great for working the higher angles for VHF contests. So this isn't a bad antenna for domestic use, and it's good enough for DXing. With the caution, though, that an antenna at this low height is going to be right down among the clutter in a suburban or an urban location, and it's going to be badly degraded by being down in that clutter. So if you're in an urban or suburban location, it's very much worthwhile to try to get above 25 feet to get out of that clutter. Well, let's look at an antenna that's much too high. My first attempt at a 6 meter antenna was an antenna at 150 feet, and that was a terrible mistake. And what happens when you put an antenna up really high is you get all of this scalloping of the radiation angles. So if you look at an antenna at 100 feet high, and there are people in our local area that have their 6 meter antennas 100 feet high, there will be times when it works pretty well for DX, but even at 4 degrees elevation angle, which is important for working DX, it's already 3 dB down. And for all these angles around 5 degrees that are important for DX, a 100-foot high antenna is in its deep null. So this is not really the best thing to do. And you can accidentally get into this trap if you're on a mountaintop. If your antenna is located right at the edge of the slope, even if it's only 25 feet high, it can appear to be 100 feet high. So you've got to be careful on a mountain where it could actually hurt you. This 100-foot high antenna is definitely too high for most sporadic E. Okay, let me go back just a moment here. Okay, so for the rest of the presentation, hang on a second. I think I have the wrong version of this. No, this is okay. So for the rest of the presentation, we're going to be talking about front to rear ratio. And that's a little different than the term we usually hear is front to back ratio. And what front to back ratio is defined to be is the radiation directly off the front of the antenna compared to the radiation directly off the back, 180 degrees away. But for many antennas, the strongest undesired lobe is not directly off the back. So this is simply a matter of definition, and front to rear is defined to be the radiation off the peak main lobe of the antenna compared to the strongest lobe anywhere off the back 180 degrees. So when you see front to rear ratio in the rest of the presentation, this is what it means. So ground gain. Antennas at the correct height produce 6 dB of ground gain in an ideal case where there are no irregularities in the area in front of the antenna. And I'll define what that area is in just a moment. But ideally, to get as much of this ground gain as we can get, at 6 dB is a lot. We prefer that terrain irregularities be less than 25% of the antenna height. That's why higher antennas are good, because the terrain irregularities proportionately are smaller. So if you have 20-foot terrain irregularities, that's really bad for a low antenna, but it's not so bad for a higher one. And the reason that you have problems with ground gain in urban areas is that the buildings tend to be large compared to our antenna height. So you like to have your antennas about 4 times higher than all of the building clutter around your antennas. And that also applies to dense forests, not individual trees, but if you're in an area where there's a dense forest, if it's near the antenna, that can be a problem on 6 meters. And we don't care very much about this stuff if they obstruct less than about 5% of the reflection zone. And this is why less densely populated areas are good, especially for 6 meters, because even though we will certainly have obstructions in the reflection zone, but there aren't very many of them, so they don't have a big effect. So these are kind of the 4 aspects of problems that affect our ability to get this 6 dB of free gain. So what does this look like? Well, a lot of us have heard about this thing called an image antenna. And it's an imaginary thing. You know, you can't, the location of the image antenna when we use it to do elevation angle calculations, and all the antenna modeling programs do this. If your actual antenna is 50 feet high, the calculation will assume that there's an image antenna 50 feet down. Well, don't try to bury an antenna 50 feet down and see how well it works. It won't work. What this is a simple approximation, and it's quite accurate, that assumes basically what is impossible, unless you're out in the deserts of the West. And that is, it assumes that the ground is perfect. It has no obstructions of any kind, and it's absolutely flat. We don't have any of that around here. So this assumption that's used to produce these simple antenna models is not accurate. But it's good enough to get a pretty good estimation of what our antenna radiation patterns look like. What the actual reflecting zone looks like, I'll show you its shape in just a moment. So you might ask, well, how large is that reflection zone? It's certainly not a single point. Definitely is not a single point. What's the shape of that reflection zone? How far in front of my antenna is it? How badly do obstructions degrade it? And how much does irregular terrain degrade it? Well, these answers are known to pretty good accuracy, not perfect, but pretty good. And this is what the reflection zone is. It's known as a Fresnel zone. It was defined for optics, but it applies to electromagnetic radiation as well. There's a very good paper that describes how this applies to the selection of HF sites, and the URL is shown here. And the Fresnel zone is defined, so we're not guessing as to what it is. It is defined to be all of the ground reflections in front of the antenna that produce reflections within plus or minus 90 degrees of the phase of the direct ray. So the direct ray is the radiation from the antenna that goes up towards the ionosphere. And the reflected ray goes down to the ground and then goes up to the ionosphere. So the Fresnel zone, by definition, is every single reflected ray that is plus or minus 90 degrees. And what does that look like? Well, in terms of the reflected rays that are right on the edge, so these are the ones on the edge of the Fresnel zone, they're right here, and I just showed a few. But it turns out they're exactly 90 degrees out of phase at the edge here, and those are the rays that produce the deep null. Let me just go back and explain what that is. So the deep null is right here. So that part of the Fresnel zone right on the edge produces this area here. So we're a DXer, we don't really care about that. We care about more like the rays that produce the peak. And what that looks like in this reflection zone is about the middle half of the Fresnel zone is the part of that reflection zone that produces most of the radiation we're interested in, the so-called minus 3 dB contours of the low angle lobe. So, and ideally this reflection zone should not be obstructed, and we already talked about obstruction. So in a moment I'll describe how big this zone is. So we'd like to have buildings and forests occupying less than 5% of this reflection zone, and they should be small compared to antenna height, ideally. If you don't meet those requirements, it doesn't mean your antenna won't work. It just doesn't get quite the amount of ground gain that's available. So let's take a look at some antennas and how big this reflection zone is. So here's my favorite 6-meter Yagi, 50 feet high. So this is about a 5-element Yagi, 14-foot boom, 50 feet high. And the reflection zone is located in front of the antenna. This is the reflection zone for that main lobe, the main low angle lobe, right in the middle of the lobe that allows us to work the DX we want to work. And the edge of this main reflecting zone starts in front of the antenna about 150 feet out. This is for a 5-degree elevation angle. It starts about 150 feet in front of the antenna. So if you're a K3AJ, that's that farmer's field out behind your house. So it starts out there, but it extends out about 2,000 feet. That's a big, long distance. And there's a lot of opportunity in the space 2,000 feet long for an antenna like this for there to be dense forests, or maybe for there to be a densely crowded suburban development. But this is what that area looks like for this 50-foot antenna. It extends out about 2,000 feet, and it's about 200 feet wide. And let's look at the 70-foot high antenna. With the 70-foot high antenna, the far edge of the reflecting zone, and here we're talking about the 3 dB zone, not the entire Fresnel zone, it extends out to about 2,500 feet. So if there are obstructions further than 2,000 feet out and out to 2,500 feet, this 70-foot high antenna can actually be worse if there are obstructions out here in this far edge. But on the other hand, if there are obstructions close to the antenna, when you raise the antenna to 70 feet, the near edge of this reflecting zone extends out to 200 feet instead of 150 feet like the one at 50 feet high. So let's look at the 25-foot high antenna. 25-foot high antenna, the near edge of this reflecting zone is only 25 feet in front of the antenna, not very far at all. So if you're going to put up an antenna that's only 25 feet high, make sure there isn't a house right in front of it 25 feet away, because that's going to be in about the worst possible place. But unfortunately, that reflecting zone extends out another 1,000 feet. So if you're in an urban environment, there are inevitably going to be hundreds of buildings in this reflection zone here, which is one of the reasons why urban locations are pretty tough for 6 meters. And why, if you can get an antenna in an urban area up at about 50 to 70 feet, it's worthwhile because you get up above those obstructions. But there's a trick you can play, and this is especially useful if you're going on grid expeditions. And that is, if you can locate your antenna on sloping ground, and this particular case is where the antenna is located on sloping ground, where the ground slopes 100 feet over the 1,000-foot area of the reflecting zone. And it doesn't have to be exactly 1,000 feet. And the slope doesn't have to be exactly 100 feet, but you can get the advantage of a 50-foot high antenna with an antenna that's only 25 feet high if you have this roughly 100 degrees of slope over 1,000 feet in front of the antenna. And if you're looking for a mountaintop place, for example, you can probably find something like this. And low antennas on mountaintop locations can actually be very beneficial because, and I'll just go back a little bit, if you're in a mountaintop location and you put your antenna up at 70 feet, you have to worry about this mountain terrain going out to 2,500 feet in front of the antenna. Whereas if you're on a mountain and you can put the antenna down low, you only have to worry about the irregular terrain going out about 1,000 feet. So you can actually perform much better on a mountain with an antenna that's only 20 feet high, 25 feet high or less, if you can take advantage of that slope. But of course, for most locations, you'll have a slope in one direction and it might be flat in another direction. So this can be complicated to take advantage of. But the slope definitely works. And so this slope has converted a 25-foot high antenna into really an optimum antenna, equivalent to one at 50 feet over a flat ground. So now we're going to very quickly look at some antennas. The URL at the bottom is a very handy site. It's Lionel VE7BQH has modeled all of the antennas that their designers and manufacturers will share the data with him. So there's some antennas that are not on his site because the manufacturers have not shared the data, but many of the antenna manufacturers have. So it's useful to look at this site. And I've cherry-picked some of the most interesting antennas from his listing. There's many more of these antennas on his website. I show this 3-element Yagi because it shows what a small, lightweight antenna can do, and I'll show you that antenna in a moment. And the other ones I've picked are some popular antennas like this 5-element one made by Directive Systems. Its front to back ratio isn't that great. And then some LFA antennas, loop-fed array antennas. They tend to have, they don't necessarily have, but some of the better ones have quite good front to back ratio. And then there's this remarkable antenna designed by YU7EF. He doesn't manufacture it, but the construction information is on his website. And it has 24 dB front to back for only a 14-foot boom. All of this stuff is available online. But there's a challenge, you know, the G0KSC and the Directive System stuff and E-antennas are all manufactured in Europe. Good luck getting a European antenna delivered in the United States during the pandemic. But if you can get one, they're fantastic antennas. And I'll just quickly show some of these. 3-element Yagi is fantastic. If you could only put up a temporary antenna, this antenna weighs only 6 pounds. And I'll guarantee you that you can erect this antenna on the 24-foot mast faster than you can build it. It's so light. It's excellent for temporary use or for placing it right on the edge of some of that sloping terrain I talked about. And you can build an antenna like this easily, or you can buy it. You can work a lot of stuff with a simple antenna like this, but preferably not in an urban location. And we'll just look at some of the other antennas you can buy. This is a loop-fed array, 10-foot boom, only 13 pounds, very good front to back. Even though you can buy it from DX Engineering, it's not available because of the pandemic. This is another LFA from the same company, from DX Engineering, it's not in stock. This YU7EF antenna is documented on his website. You have to build your own. 6-meter antennas are really easy to build. Fantastic front to back ratio. And this one is a split dipole feed. It's not a loop Yagi. And this is another G0KSC antenna. If you buy it, it has to get shipped from England. Let's look at some longer boom Yagis. And one of the characteristics of longer boom Yagis is they tend to have better front to back. And anybody who tries to operate FT8 in this metro area knows that having a good pattern is a good thing, because signals can be really, really strong. So it's worthwhile having one of these higher performance antennas. But notice all of them are manufactured in Europe. Good luck getting your hands on one of them right now. I've listed one of the more traditional antennas. This is a 7-element M-squared, very popular antenna. Its front to back ratio is pretty good, but these LFAs are 5, 6, even 9 dB better. We just quickly look at that. This is a very popular 6-element Yagi from G0KSC, 21-foot boom, and this is an antenna also from his company, Nova Antennas. Fantastic front to back ratio, 27 dB. This is from a German company, E-Antennas. It's also a loop-fed Yagi. Normally, you could get this from DX Engineering, but with the pandemic, they're not in stock. This is another G0KSC antenna. Let me show you this antenna system. It's I don't know how high this antenna is, but it's a very tall tower, and it's a big waste of money. Because for sporadic DXing, almost all of the performance you need to get in terms of antenna performance, you can get from antennas at 50 to 70 feet high, and maybe in the really, really oddball case at 100 feet. So if I were to build an antenna system of this type, and I'm not planning to, but if I were, it would be a rotating tower that was probably 75 feet high, and I'd probably put a Yagi at 75 feet, one at about 50 feet, and maybe even one down lower, but certainly not one of these big tall antennas. A local hand, Al K3TKJ, built an antenna system like this, used it for a year, and decided that he had wasted his money because he discovered that all the performance he needed came off the bottom 2 or 3 antennas, and the rest of them didn't earn their keep. And I believe most of these antennas have been removed from that tower now over in Delaware. So here's another E-Antennas unobtainium antenna from DX Engineering. They'll be happy to take your money. This is the M-squared traditional antenna. It's a very fine antenna, but front to back ratio or front to rear ratio is down about 5 dB compared to the loop arrays. And this is really a fantastic antenna. Some of us have worked JA1BK. He tends to be the strongest signal from Japan on sporadic E, and you can see why. It's a pair of 8-element loop-fed Yagis stacked on this crank-up tower, and this antenna really, really works. So let's look at how you build 6-meter antennas. Half-inch diameter is a very popular size. You can buy the tubing you need from DX Engineering, even with the ends already split. The URL is shown, and usually you use 3/8 inch diameter tubing inside. When you build any antenna, whether it's for 6 meters or HF or any other Yagi antenna, it's very, very important first to clean the joints before you put them together, take the oxidation off. And then once you've done that, to put an anti-seize and anti-corrosion lubricant on the antenna. I have used a variety of these materials over the years. This is the only one that I've used that doesn't dry out and cake. And if you ever try to take an antenna apart, it's not unusual for this lubricant to become dried, and it actually makes it more difficult for you to take the antenna apart rather than easier. This is the one I've used for the last 50 years, and I've never, ever had problems taking an antenna apart when I use this one. But let me mention that it's very important to clean the elements before you telescope them together. You can use a steel or a brass brush to clean out the inside of the tubing. You can buy some of these brushes that are used to clean out gun barrels, for example, or for plumbing. And you can use something like Scotch-Brite to clean the outside clean the oxidation off the outside of the tubing. Very important to do that when you put the antenna together. And in terms of antenna booms, you can buy the aluminum tubing either from DX Engineering. Some of the material is shown here with their part numbers and URL. It's also very popular on 6 meters to use square tubing. And you can purchase this square tubing from Metals Depot and a variety of other places. The URL is shown. And in terms of mounting elements to the boom, these plastic clamps have become very popular. They're available from a number of locations. This URL is just one of many. And these are mounted on a flat plate that could be either an aluminum plate or a phenolic plate, and then that plate is attached to the boom. Another very important aspect that must not be forgotten, and that is almost all these antennas I showed you, except for the one or two of the T-Max Yagis, almost all these antennas are direct 50 ohm feed, and you cannot get the performance you've paid for out of these antennas if you just connect the coax to the split feed without a choke. And the primary purpose for that choke is RFI suppression. And that RFI can be either be in the form of noise from the local TVs and LED lights and power lines, or it can be all of the local hams on FT8 that in essence are RFI for us trying to listen on these very crowded FT8 chunks. So if you want to get the full benefit of the front to rear ratio of your antenna, it's important, very important to put a choke on. If you're in an environment where there isn't a lot of RFI, a simple close wound choke is a good idea. 4 turns close wound is fine on 6 meters, but there is a little bit of an issue. And that is that the manufacturers of RG213 do not control the interwinding capacitance of the jacket of their cable. So when you build a choke of this kind, it's necessary that you measure the resonant frequency of the choke. Otherwise, you don't know where its performance is optimized. And these coax wound chokes are fairly narrow band devices. So if you just wind 4 turns onto a form, you might wind up at 40 megahertz or 60 megahertz instead of where you want to be. You can also buy higher performance chokes, or you can make them. This is a ferrite. These are ferrites slipped over RG213. You can buy the cores from DX Engineering, and there's the URL, or you can purchase the entire pre-manufactured choke from Innov Antennas in England. Good luck with the shipping, but you can buy the whole thing pre-manufactured. And K9YC, very talented engineer, has developed a very, very high performance choke for very severe RFI environments, and his URL describes how to build it. It's very easy to build. So let's look at coax cable. You know, on 6 meters, coax cable really makes a difference. The losses are very significant. For example, if I were to put a Yagi on an AB577 at 50 feet, kind of an ideal situation, well, by the time I have a rotation loop at the top of where the rotator is and I come down to the bottom of the AB577, I've already gone 60 feet. So I've already encountered 1 dB of loss with my RG213, and chances are my radio is not at the base of the AB577. So pretty likely, if I'm using RG213 for my entire installation, that I've got at least a couple dB of loss, and maybe more than that. Well, there are many types of hardline that come available at Hamfests, or you see available for free from other friends. LDF4 is a very excellent choice, commonly available at Hamfest for less than $1 a foot, and it's an excellent choice on 6 meters. And why do I say that? Well, if you want to step up to the next larger cable, LDF5, you have to go 475 feet before you can gain a dB on LDF4. There are other good choices too. LMR 600 is another good choice. Performance is about the same. RG213, unless you're putting your radio right at the base of your 50-foot pole, it's probably not the perfect choice. Coax cable connectors. On 6 meters, N connectors and UHF connectors are commonly used. They both have insignificant loss. I defy you to measure the amount of loss in such a connector. It's very, very low. For most hams, it's easier to install a PL259. But quite honestly, I would say for most hams, you're better off getting a commercial company to install your connectors, because if you look at connectors that are installed by hams, you see an awful lot of stuff that you wish you never did see. All kinds of hacking going on. End connectors for many, many years were manufactured with pins that were separate from the connector body. And there's a problem with that. And that is, unless you have precision instrumentation, chances are you're not going to be able to place that pin plus or minus a half a millimeter to meet the manufacturer's depth tolerance. And what happens if you don't meet that half millimeter placement requirement? If the pin is not deep enough in the connector, the mating force with the mating female pin is not adequate to produce a reliable connection. And you say, well, okay, so I'll err on the long side and I'll allow the pin to be maybe more than half a millimeter too long. Well, unfortunately, there's a shoulder on that pin. And if it's too long, it will damage the mating female connector, permanently damage the connector, and maybe even break one or more of the leaves off. So if you have put end connectors on your coax and you did it with loose pins, chances are you didn't meet that depth tolerance requirement. And chances are, as a result, you've got an unreliable connector. Thankfully now, many end connectors, both for hardline cables and for RG213, are sold with captive pins. So the manufacturer sets the tolerance and sets the precision alignment of the pin, and those end connectors are very reliable. But the old loose pin ones are probably best removed from your system. If you do use PL259s, and there's no reason not to use them on 6 meters, they're very fine connectors. I always recommend tightening them, but don't overdo it. I tighten them just enough so they can't be removed by hand, just enough. That's usually about a quarter of a turn. Unfortunately, I've seen some people have taken my advice in this way, and they use so much force on the shell of the connector that the shell has gotten deformed. So you can take this advice and turn it into terrible advice if you put too much force on it. And this is what the high quality PL259 looks like. This is the only one I ever use in my station. They cost a couple of pennies more than the cheap Hamfest ones, but these have very consistent reliability, and it's an excellent connector on 6, as are the end connectors with captive pins. And what should the end of the cable look like where it attaches to the split feed on your antennas? If your split connection at the end of your coax doesn't look like this, make a note when you take your antenna down to work on it to make it look like this. Notice there is absolutely no visible trace of any of the coax connector center conductor, copper center conductor or dielectric, and no trace of the shield and no trace of the outer jacket. It's all been covered. And I always use Scotch 130C. I'll show you that product in a moment. Unfortunately, Scotch 130C, it's a self-vulcanizing rubber tape. Its UV resistance is not good. So I cover it with a couple of layers of Scotch 33, and that's what this is showing in this. So if your antenna doesn't look like this, you got a home project for this summer. And if it does, it's probably going to last for 10 or 15 or 20 years. And your coax is going to last that long also. And when you connect it to the driven element, one of the challenges is to connect it in such a way that you don't create a dissimilar metals problem. And the way you do that is by using a stainless steel screw passing through the each side of the driven element. And you attach the solder lugs, well, the lugs on the coax connector, you attach them to the stainless steel screw, but they should not be in contact with the aluminum of the antenna. So you notice if you examine this closely that there's a nut that fastens the bolt, or fastens the screw to the aluminum, and then there's a few threads that nothing's attached to, and then there's another nut and another, and then the lug and a external tooth lock washer that really assures that you get a really good electrical connection. And then I use nylon insert lock nut, common trade name is Nylock, so that this thing doesn't ever come apart. This kind of a connection to your driven element will not corrode. I don't guarantee it on the ocean front, but in central Maryland, it will not corrode. And it will last 15 or 20 years, just like the well taped up coax will. And when you get done, cover the whole thing with liquid electrical tape, and it should look like this when you're done. And this is my last slide. This is what the waterproofing products look like that I always use. I always use linerless rubber splicing tape. You can buy versions of this rubber splicing tape that have a liner, and I find it difficult on a tower to manage that liner. It's a thin piece of plastic that's between the turns of the tape, so I don't use the stuff with liners. I use this linerless tape, readily available from Home Depot and countless hundreds of other places. It's applied to the connectors exactly according to the instructions with the tape, and that is that the sticky side is facing out. And you stretch the tape to about 50% of its original width. You can tell when you stretch it just right because the color of the tape changes from black to sort of a gray color. This tape is not made out of gold. And I see hams putting electrical tape on things and they overlap at about 5% or maybe 10% so that they get to use more tape. But tape doesn't work unless it's overlapped. So when you apply tape, whether it's for this application or any other, it should be overlapped 50%. So it's not made out of gold. It's just plastic, guys, and overlap at 50%, not just a little tiny amount. And then it will work. If you overlap at 5% or 10%, you just wasted that tape that you put on there. And here are the URLs. And that's the end of my presentation. So I've probably given everybody a little bit of homework for this year.
You certainly have. You certainly have, Frank. So let's open it up for questions. Anybody have questions that they want to address to Frank? It's been a great presentation.
I have a question.
Shoot.
What direction do you put the beam in when it's going there all day?
I'm sorry, I don't understand the question, Bud.
What position, north, south, east, or west, do you place your rotator so that the antenna is pointing in some direction? I don't know what direction to put it in.
It all depends where that sporadic E patch is. Who knows? Yep.
Anything else?
But but of course you know the answer to that question, Bud. And it wasn't really covered in this presentation. And that is, we have this wonderful tool called PSK Reporter. So we can see what's on the air. We can see who else is working things, and that'll give us a pretty good idea if there's an opening and if we're lucky enough to have a sporadic E patch in the right place.
Hey Frank, this is Tom, K3AJ. I sent you a question. I sent you a question in the chat window.
I'm not monitoring the chat window, so you'll have to actually use your voice.
Well, you could click on it. Okay, so my question has to do with vertically stacked antennas. I always thought that vertically stacked antennas gave you a lower angle of radiation. So I was wondering if you could compare, say.
So erase that thought from your mind permanently.
That's just my question.
No, what you always thought is wrong. And let me I don't want to spend a lot of time elaborating on that because the purpose of this presentation was not to deal with stacks, but let me just go to a slide and illustrate the point. So here's a really nice antenna. This is a 5-element Yagi on a AB577. It's really kind of the best 6-meter antenna you can ever hope to have. But the only problem with an antenna like this is that we waste all this power in these upper lobes. And what we can do when we stack two Yagis is we can extract most of this power, and it's mostly these next two lobes that have most of the power. We can extract that power from those wasted upper lobes and place that power into the low lobe of the antenna, and that is what stacking does. And the reason there's often this misunderstanding, and your misunderstanding is not uncommon, is, of course, when you stack two antennas, chances are, let's say, if your bottom antenna was at 50 feet, a really good choice. If you're going to stack another antenna, chances are you're going to put it 15 or 20 feet above rather than 15 or 20 feet below. So what you've done is you've moved the center of radiation from this array from 50 feet up to an average height of about 60 or 65 feet. So you've actually raised the antenna array when you do the stacking. And there's a fancy engineering term for that. It's called the phase center of the array. And it turns out that's located just a little bit less than halfway between the two. So the concept you had in mind of stacks producing lower angles isn't really true. But what actually happens with stacks is usually their phase center is higher than a single Yagi, so that's why you get lower angle radiation. And the other nice thing you get is that all this wasted power up here gets sucked out of these high angle lobes and gets added into that useful low angle lobe where we make all of our money doing 6 meter DXing. Did that answer your question, Tom?
Sort of.
Sort of. We could have.
I mean, I was with you till you made that last statement.
Well, we could have a discussion over a sunshine burger someday.
Well, I mean, I was with you until you made that last statement that said you suck the power out of those useless lobes and put it in the lower lobe. And I thought, well, isn't that what we were talking about?
So anyway, so Tom, if I only increase the power in this lobe, the low angle radiation would only increase by a dB or something like that. But what actually happens is the antenna is usually higher. So it's the lower angle radiation really comes out of the increased height of the pair of antennas. Next question. Don't be shy.
Say again?
I have a comment and a question, but I'll wait in line.
Well, you're at the head of the line, so go ahead, Mike.
Okay. Observation. I'm probably one of the few within all of PVRC that my 6 meter antenna is a vertical, and that's what I've got. That's all I can use here living in a townhouse, but it is up about 40 to 50 feet.
Yeah, so it's at an ideal height. Yep.
Over 20 years, I have worked about 330 grids on 6 meters with that vertical antenna, one of which was Pitcairn Island. I've got the card to prove it. Now, I have a question. In your presentation, and I'm going to use this information for if and when I ever move out of this damn townhouse and get into some place where I can put up some aluminum. I'm going to go back and review this and use it. But you made a comment about the end connectors, but I've never seen 6 meter antennas with an end connector hookup.
Oh, well, you haven't.
They've always been PL259s.
You haven't looked real hard. A lot of hams have this preconception that on 6 meters you should be using end connectors, and any of them who've put these loose pit end connectors on them most of them have screwed up. And some of them will say, well, look at this connector, it looks great. Well, sure, but you're the 1 out of 10 guys that knows how to do it right. It's like any other highly skilled trade, and putting connectors on is certainly a trade. It's like any other highly skilled trade. If you do it every day, you'll get it just right. But if you're a once a year plumber working on your bathroom, chances are you're going to cause a flood instead of the highly skilled thing that you pay your plumber to do. So it's the same thing with connectors. It's a highly skilled trade to put connectors on correctly, and most hams don't get it right, whether it's an end connector or even a UHF connector. And I'm sure you've seen connectors where the hams have hacked on in all kinds of ways that you never believed anybody would ever do, but they do it all the time.
In selling coax with connectors on it for 17 years, after this many connectors, I'm doing a pretty decent job. I haven't had any come back complaining about it, so I guess I'm doing a good job.
That's good. Do you sell coax cable with end connectors on them?
Yes, but usually I can't do the end connectors that well. So the people I buy my coax from, they do a great job. I'd rather take a little bit less loss and have a good product.
Yeah, well, that's right. Well, and the real critical specification is this plus or minus half millimeter spec on the center pin. And Mike, you know, when you buy these connectors, you really ought to have a depth gauge to check that the people that are installing those connectors are doing it right. It is a critical tolerance.
They have some testing mechanism that they put every piece that they build, they actually put it through a test.
Yeah, good.
I've seen them doing it.
A lot of us, if we're mechanically inclined at all, might have a depth gauge, and it's worthwhile.
Right.
To just put that depth gauge on an end connector, and if a ham is installed, the chances are it's going to be wrong.
And the other problem with the loose pin end connectors is getting them centered too, because it's hard to get the centering just right. If you don't get it just right, it can mess up the connector, or at least get the pressure uneven around it. Don't get full connection all around the whole pin.
So Tyler, tell them your end connector story on your tower 100 feet up.
Well, we still haven't figured out why it failed, but this Prodlin hardline I'm using, it's like it's an oddball. It's like 1.25 inches, I think, or something. But the guy in Pennsylvania was FRC had a pile of it, and I bought some for FRC. And this machinist they had up in Pennsylvania was machining the end connectors for it, and it works quite well. But you have the pins, you know, if you don't get the pin depth just right, like you don't use the depth gauge and you don't get it centered quite right, it can cause problems. And well, I've had them on my tower for 25 years or whatever, but we finally had a problem with the 40-meter feed, and because of where it's inside the tower and everything, because we pulled it up. I assembled all the connectors on the ground and then pulled the hard line up through the middle of the RG Roan 45. So it's nearly impossible to work on them, as we discovered, or Frank discovered this year. But I started having a problem. I was running, FT8, running full power in the middle of the night, and all of a sudden my power started going away, and something had happened to that pin. But we lucked out so far. We were able to stack a couple of coax adapters, like N to what I guess it was N to UHF, and then back from UHF to N. And so when we stacked those adapters in the line, and magically the connection came back. But that's pure magic. And the other thing is I use a lot of pin connectors on my CATV hardline. I guess with 1/2 inch or something, you can use UHF connectors directly, use a barrel or something. But most of mine is 3/4 or larger. So I use pin connectors, but the pins aren't captive, and it's a real pain to get it just right. And I haven't that's the first one I've had fail in 25 years, but I was very careful about putting them together, and it's not serviceable the way it is installed on my tower. So it's like Frank said, anything at 6 meters and below, unless there's some real good reason to use end connectors versus UHF, you're much better off with UHF, and the RF won't care.
Yep. And the other thing is, and if you can possibly avoid it, don't use female end connectors on a tower, because if damage does occur, it's going to be the female that's likely to get damaged. And if you have a pair of male connectors, end connectors on the tower joined by a end connector barrel connector, then if you damage the female pins in the barrel connector, well, you could throw away the barrel connector and put in a new one. But if it's a female end connector on the coax that got damaged 100 feet up the tower. If you're paying somebody to do that work, you're going to pay a lot of money for that mistake. So I recommend for those people who need to use end connectors on a tower to never, ever use female ends up on the tower. Never. Use the males only. And then use a barrel connector to join them. Any other questions before we shut this off?
Hey, Frank, I've got two maybe silly questions.
The only silly question is the one not asked.
First, you mentioned earlier in your presentation that the activity in the E layers is kind of generated by meteors or meteorites.
Meteoroids.
Meteoroids.
Think-
And then you
think
mentioned
dust.
that really the peak of the season is May through towards the
Mid-
middle end of
Mid-May
into
to
July.
mid-August.
So I guess the question is, why do we not see peaks around the times of the Leonids and the Perseids meteor showers?
Because the meteoroids, there isn't much variance in the influx of this dust-like meteoroids. There isn't very much variance at all, day to day, season to season. The meteors vary, but the meteoroids that we care about for sporadic E really don't vary at all.
Okay. All right. That's the first question. Second question is, I know that there's some discussion on 6-meter reflectors and elsewhere that I know we talk about the E layer being in the range of 100 miles up, but people are making the claim that during periods of very high thunderstorm activity where you have the tops of the thunderstorm clouds into the troposphere at 10 to 15 miles in height, that there is enough disturbance electricity wise and wind wise caused by very severe thunderstorms that it may have a propagation effect on 6 meters. I want to get your thought on that.
That is true. Let me correct something I said because it was not correct. There is an annual variance in the meteoroid and meteorite influx. And in fact, you can see one of the big meteor showers right here. So there's this annual variation, but these big meteor storms that occur like Perseids, for example, and others, they hardly affect the influx of meteoroids at all. And then your other question, this is the effect, and that is any major disturbance in the atmosphere, it can even be hurricanes, tends to cause an exaggeration of these atmospheric tides, and that can create forces on the bottom of the of this region where these patches occur that make them even denser, which increases their MUF. So in June and July, it can cause their MUF to go up to 70 or 80 megahertz, or in the non-optimum times of the year, like December and January, it can cause MUFs that would not be usable on 6 meters to be usable on 6 meters for 15 minutes or 30 minutes. And there are many major atmospheric events like thunderstorms and like these atmospheric tides that are there every day that cause exactly what you described. I'm not sure it's the electrical part though. I think it's the compression, the wind shear. So exaggerating the wind shears, I think, is what's going on. But this is you could get a PhD in this topic if you wish.
Great, thanks.
Do we have any more questions for Frank?
Where'd I get my AB 577 to put my 50-foot tower, 50-foot support up?
Well, if you read the PVRC email reflector, you'll discover that there was one offered for sale a few hours ago.
Yeah, I know. I haven't heard back from him.
Probably too late. Well, you
Probably.
already contacted him.
Well, I
Good.
emailed him back. I didn't call him.
You know, as I
He didn't seem to
mentioned
be
to Hans,
definitive if he had one. He was like, maybe I have one.
Yeah, I know.
he has to decide if he wants to sell it.
He's got
He
a
has-
dozen of them, doesn't he?
Yeah, he's got a dozen. AB 577s are kind of a special thing. It's the only thing you'll ever buy in ham radio that you will not lose money on. So even though they've gotten to be expensive, when the time comes to sell it, you'll get your money back. It's an
I
investment.
got one.
Almost anything else we spend money on ham radio, especially computers, we lose a lot of money on, but not AB 577s. Okay, guys. If
Thank you,
anybody
Frank.
has any questions,
Thank you,
just send it, just drop me an email. And Ted, let's find a way to post my slides somewhere on the PVRC reflector so people can look at them.
We will certainly do that, and I will pass out the link for this recording